So in today's video, we're going to look at one of the most important results in complex numbers so far. We're going to do a quick bit of a refresh on some results that we'll need, and then we'll dive straight into it. So any complex number cos theta plus I sine theta, recall we can write that in shorthand as cis theta. And furthermore, remember that if we multiply two complex numbers together, z and w say, then the argument of that product is just equal to the sum of the arguments. So let's suppose we have two complex numbers, z and w, and they're really the same number, cis theta. Then zw is z squared. We add those two arguments together and we get cis 2 theta. Now let's suppose that w is z squared. Then this time, zw is z cubed. So we add those arguments together, theta and 2 theta, and we get cis 3 theta. And hopefully you can see that there's a nice pattern here, that z to the power of n is just cis of n theta. We just multiply the arguments. And this has a very special name called the Moivre's theorem. So in general, if z equals cos theta plus I sine theta, then for any positive integer n, z to the power of n is equal to cos n theta plus I sine n theta. And in fact, n doesn't actually have to even be positive. It can be a negative integer as well. Now we will prove this result, but we're going to wait till you've finished your work on induction in extension 1 before we go through that. So let's run through some simple examples and you'll get to see the power of de Moivre's theorem. So let's suppose that z is equal to negative root 3 plus I. What we're going to do is write that in mod arg form first, because we need that for de Moivre's theorem, and then we'll be able to use de Moivre's theorem to evaluate z to the 7. So hopefully you remember how to find the modulus and the argument. Here the modulus of z is just the square root of negative root 3 all squared plus 1 squared. You just square the real and imaginary part and then take the square root. It's basically Pythagoras. And the modulus here is 2. The argument of z, we need to consider plotting the point in the argand plane, and then find the auxiliary angle and then adjust for which quadrant it's in. So here the argument would be 5 pi and 6 because it's going to be in the second quadrant. So that means that z here is equal to 2 times cos 5 pi and 6 plus I sine 5 pi and 6, or in cis notation, 2 cis 5 pi and 6. Now it's easy to find z to the power of 7 because we have seen from de Moivre's theorem we just need to multiply the argument by 7. Now de Moivre's theorem is set up for a complex number where the modulus is 1, but the nice thing is that if the modulus is anything but 1, all we need to do is find the power of the modulus, and then the process is exactly the same. Just multiply the argument by whatever the power is. So in this case, z to the 7 is equal to 2 to the power of 7. We take the power for the modulus, but then we can use the multiplication rule to find the argument. So z to the 7 is 2 to the 7 times cos 7 times 5 pi and 6 plus I sine 7 times 5 pi and 6. Or breaking that down to the simplest case, z to the 7 is 2 to the 7 cis 35 pi and 6. Okay, I've written it in long form there, but for simplicity, let's just talk about it in cis notation. But our argument really, to make it unique, needs to be between negative pi and pi. So we've got to keep subtracting multiples of 2 pi to keep coming around the circle to get as simple as we can. And if we do that, keep subtracting 12 pi on 6, then we end up with the argument actually being negative pi on 6, the principal argument being negative pi on 6. And if we then evaluate what that is, so we actually work out what cos of negative pi on 6 is and what sine of negative pi on 6 is, then we get that z to the 7 is 64 times root 3 minus I. Okay, and we do need to be able to go to that final step. If they give us a complex number in standard notation, then our solution needs to also be in standard notation. We used mod arg form along the way so that we could exploit de Moivre's theorem, but we need to put it back into the standard form at the end. Another example, what is the smallest positive value of k for which z equals 1 plus I to the power of k is purely imaginary? So we're going to be able to exploit de Moivre's theorem nicely here. So again, we need to be able to write 1 plus I in mod arg form. So z in mod arg form is root 2 times cos pi on 4 plus I sine pi on 4. So z to the k then is root 2 to the k times cos k pi on 4 plus I sine k pi on 4. And to be purely imaginary, that real part must be 0. which means that k pi on 4 must be an odd multiple of pi on 2. Think of your cosine graph. The only way that that can be 0 is at multiples, odd multiples of pi on 2. And what that means is that k pi on 4 is equal to 2n plus 1 pi on 2. And notice the k and the n are different, and that's because they have to be, well, they don't have to be, but they to be general, they should be independent of each other. They might be related, but they might not be. So we've got to keep them separate to keep it nice and general. So that's why we're using a k and an n term there. And that's nice and simple to break down. We can cancel out the pi's. We can multiply across by 4, and then 4 and 2 have a common factor. So that ends up implying that k is equal to 4n plus 2. Now, if we try a few values of n, because remember we want the smallest positive value of k. So if I let n equal -1, then I get k is -2. So that's negative, that's no good. That doesn't work. What about n equals 0? Well, that gives us a k equals 2. That's going to be the smallest value because k was negative when we had n equals -1, and now it's suddenly positive. So that's the smallest positive value for which 1 plus I to the k is purely imaginary. So we've solved the problem. So that's it for this lesson, looking at, like I said, a very powerful theorem, de Moivre's theorem. Hopefully you can put it into practice in the exercises. And then next lesson, we'll use de Moivre's theorem again to prove trigonometric identities. It turns out that now that we've unlocked the door to complex numbers and we've unlocked the door to de Moivre's theorem, suddenly really complicated trigonometric identities that otherwise would be really difficult to prove become fairly easy to prove. And therefore, once we've proven them, we could use them in other contexts, such as integration, where integration is a really difficult process. We really need, but basically, we don't have a general theory for integration. We just need a big toolbox with lots of tools in it, and we use the appropriate tool at the appropriate time to try and integrate. So if we can come up with a whole heap of new tools to put in that toolbox, fantastic. Thanks for watching.